Good morning. This is Muhammad Hawa. We continue our lecture series in signal analysis by reviewing some important and basic signals. I'm hoping you remember the signals we're going to discuss here because we want to use them in examples later on. So please remember them, memorize them, make sure you understand their properties. We'll continue with more signals hopefully in the next lecture as well. Our first function or signal x of t that we will start with today is the linear line. The linear function or linear line or simply line or straight line. This is very basic signal that you're familiar with. The equation for x of t is m by t, where m is called the slope or the gradient. The slope or the gradient of the signal. So m, the slope multiplied by t, plus b, where b is the y-intercept. It is where the signal hits the vertical axis. In my case, I'm using x of t, so maybe you want to call it the x-intercept instead of the y-intercept. The parameters for the linear line are easy to understand, are easy to calculate. For example, to find the slope or the gradient of this linear line, all you have to do is take 2 points at that linear line. Let's say I take t1 and x1. I also take t2 and x2, and then you find the difference between x2 and x1. That's delta x, you can see here. And then you find the difference between t2 and t1. That's delta t here. If you divide delta x by delta t, what you're getting is the slope of that linear line or that linear function, which is x2 minus x1 over t2 minus t1. Any 2 points would work just fine over this line to find the slope. If you want the y-intercept, it is the point where the linear line hits the vertical axis, x of t here, and that's called b. So it is the point of x of t where t is equal 0. So you take the equation x of t and substitute t equals 0, 0 time. If you substitute 0 here, you multiply it by the slope, what you're getting is 0, and you end up with the value, the constant b, that's the y-intercept. Here, I wanted to show you quickly the effects of changing the slope and the effects of changing the y-intercept. In the first diagram, you're seeing here, I'm just going to change the slope. Notice the difference between the red curve, where my slope is 0.2, and the blue curve, where I change my slope to 0.5. Notice that this is a higher slope, so the linear line increases at a faster rate. This is the effect of a higher value of slope. Notice that the y-intercept is still the same, equal 1. If I want my line to go even faster with increasing time, then I increase the slope. So notice if I increase from 0.2 to 0.5 to 1.5, the black curve is going way faster up with increasing time compared to the other curves. If you take a slope of negative, like in this case minus 1.2, notice that the curve is now decreasing rather than increasing. But all those curves have the same y-intercept, so they cross the vertical axis at exactly the same point, which is the y-intercept. Here, I show you the effects of keeping the slope constant, but changing the y-intercept. I increase it from minus 1 to 1 to 3, and you can see my crossing here, instead of minus 1, happens at 1 and then happens at 3. But the rate of change, the slope, the increase rate is exactly the same for all the curves. I want you to remember those things whenever we talk about linear lines, and also remember those things for the other signals we're going to discuss in this lecture and the next one. And this way, whenever we solve an example, it's easy to visualize in the back of your head what's going on with our signal. And the best technique I can propose for you to remember those things is to draw those curves by yourself. Don't just look at the curves I gave you, try to actually draw the curve yourself. For example, take some points in time. Let's say t is equal minus 1 second, t equals 0 second, t equal 1 second, t equal 2 seconds. And then take the equation x of t, for example, in this case, linear line 0.7t plus 1, and then start substituting the different t's within each equation. For example, at t equal minus 1, what is x of t at t equals 0? What is x of t at t is equal 1? What is x of t at t equal 2? What is x of t? And start drawing points over the curve and then connect them with a dot. This way you see the curve yourself, you remember the curve, you remember the properties, and maybe change the slope, see what happens, change the y-intercept, see what happens, and so on. And this way, you understand the different properties of the curves and you never forget it. Please try to do this for the linear lines I've given you. Also try to do this for the other curves I'm going to show you in this set of slides. This way you're ready for later examples. One last thing about the linear line. If I ask you, when does this linear line cross the time axis? When does it become 0? When is x of t actually equal 0? What point of time t naught where x of t naught is equal 0? This is easy to find. All you have to say is, let me substitute in the equation t naught where I want the result of the equation to be 0. This is called the 0 of the function or the 0 of the signal. And then you equate the equation mt naught plus b. That's the equation where you substitute t naught and you know that you want the result to be 0. And then you can easily find t naught by moving b here and dividing by the slope. So the 0 of the function occurs when t is equal to t naught minus b over m. Let me give you a couple of exercises for you to practice. In the first example, I will give you the slope, m is equal 5.5. And I'll give you the y-intercept, b is equal minus 2.5. So you can easily write the equation for this linear line. Now use this equation to draw the corresponding linear line. And also use that equation to find the 0 of this signal. In the next exercise, I want to give you 2 points, and I say those 2 points lie on the linear line. t1, x1, that's 2 and 1. And then t2 and x2, that's 5 and 7. So 5 seconds, you get a value of 7. From the knowledge of those 2 points, please write the equation of the linear line and also determine the slope and the y-intercept. And then from that, draw the linear line. With that knowledge, let's look at some special cases. A very interesting case is when x of t equal t. X of t equal t. This is just a linear line. You should know that because x of t is equal to t has the same equation as the linear line. All I did is substitute the slope m equal 1. As you can see here, the slope is 1. And I added 0 for b. That's the y-intercept because the line crosses the vertical axis at the origin. Another special case of the linear line is if we make the slope equal 0. If we make the slope equal 0, it means the line is not increasing and the line is not decreasing. Rather, the line is constant. It does not increase or decrease with time. This is what we call constant signal or constant value or DC value, just like direct current. It has constant value. So constant signal or constant value or DC value where that value is equal b, the y-intercept here. Notice here I give you different curves. For example, this is x of t is equal 5. That's a constant value. It's actually linear line with 0 slope. But the y-intercept is 5, so it crosses the vertical curve at 5. Here, the y-intercept is 2. That's a constant 2. The constant could be 0 as well, and it lies over the time axis. The value could also be negative, like in this black curve. Moving on, another curve that we're interested in is the parabolic function. Notice instead of t, I'm going to use t square. T square, that's the parabolic function. However, I could have some constants associated with the t square. For example, this scaling constant a, this shifting constant minus c, and this shifting constant plus b. And this one is called the parabolic function. We could simplify and put 0 for that vertical shifting parameter. We could use 0 for that horizontal shifting parameter, and we could use 0.5 for the scaling factor. We get t square over 2. This is what we call unit parabolic function. It's the very simple, very basic parabolic function. I want to show you the effects of those constants a, b, and c on the shape of the parabolic function. But before I do that, maybe you can answer me a question. What parameters should I be changing to change the parabolic function from being concave up to being concave down, or from being concave down to being concave up? Please pause the video and try to think about it before you see the results. In this diagram, I show you the effects of changing the scaling factor a on the parabolic function. I'll start with the red curve. X of t is equal 0.5 t square. That's the simple unit parabolic function. And then I'll go on and change the scaling factor from 0.5 to 1. I'll get 1 t square. You can see the effect over the blue curve here versus the red curve. It goes faster to infinity. And if you increase the scaling factor 2, you go to infinity even faster. But all those curves are concave up. If you change the scaling factor to negative, minus 0.5t square, what happens? This curve is now concave down. It's very similar to the red curve, but the red curve is concave up, the black curve is concave down. This diagram, on the other hand, shows you the effects of the vertical shift and the horizontal shift. Let's start with the red curve again. The red curve is 0.5t square, so the shifting parameter here is 0 and the shifting parameter here is 0. If I set the horizontal shifting parameter to minus 6, so 0.5t minus 6, the whole thing square, what happens is that I shifted my curve to the right by a value of 6 seconds. If I substitute 0.5t plus 2 square or t minus 2 square, then I shifted my curve by a value of minus 2, and that's the shift to the left. Now compare this one with this one, the blue curve with the black curve. They're very similar. 0.5t minus 6 square, 0.5t minus 6 square. They are extremely similar except for this vertical shifting parameter where I use minus 3 here. Once I use minus 3, the curve is shifted down by a value minus 3. All right, we talked about the parabolic function. Now let's talk about another function, but this one is a homework for you guys. Try to figure out what this function is. It is the same function. I just use different scaling factors here between the red, blue, green, and black functions. So please try to figure out what function is that. The next important function on our list is the exponential function. Here, I'm going to assume an exponential function with a real number exponent. Later on, we'll talk about the exponential function with complex number exponent, but we'll leave that for a later lecture. The exponential function has two types. There is the increasing exponential function. You can see it increases very fast. And then there is the decreasing exponential function or the decaying exponential function, and you can see it decreases fast. The equation includes an exponential here, alpha e to the power kt, where alpha is a positive constant and k, the exponent, is a positive constant. Notice that when t is equal 0, you get e to the power 0, that's 1, you get alpha. That's why the increasing exponential function hits the vertical axis at alpha. When t equals 0, you're getting alpha, but then you start increasing fast. The difference between the increasing exponential and the decreasing exponential or decaying exponential is that you're getting alpha e to minus kt, where k is positive, so this exponential has a negative here, and what you end up with is a decaying exponential, which also crosses the vertical axis at alpha. What is the effect of the exponent k and the scaling factor alpha on the increasing and decaying exponential? We see the effects in this diagram. Notice here the red curve, which is a 3e to the power minus 0.2t. So the exponent here is minus 0.2 because it's negative. It's a decaying exponential. What I changed between this red curve and this blue curve, which is 3e to the power minus 0.5t, I increased the value of k minus 0.5, so the exponential is decaying faster. It's going to the steady state or zero value way quicker than the red curve. If you increase the exponent even further, this is e to the power minus 2t. I increased it from minus 0.2 to minus 2, that's tenfold. So you get way faster drop in the exponential. The scaling factor is a little bit different. Please compare the red curve, which is 3e to minus 0.2t, and this black curve, 7e to minus 0.2t. So it's the same exponent, but I increased the scaling factor to 7. So it's the same red curve, but scaled up. It's multiplied by 7 rather than multiplied by 3. Here, I show you the same thing, but for the increasing exponential. Please notice the difference between the red curve, where the exponent is 0.2, and the blue curve, where the exponent is 0.5, and the green curve, where the exponent is actually 2. So it's a tenfold increase compared to this. What happens is that you increase the value way faster, the exponential shoots up quickly to way higher values going to infinity. The scaling effect can be clearly seen by comparing the red curve and the black curve between 3e to the power 0.2t and 7e to the power 0.2t. But all of those are increasing exponential because the exponent is positive. A homework for you guys: what happens if I change the scaling factor to negative? I keep the exponent positive, 0.2 or 0.5 or 2, but I want to change the 3 into minus 3 or the 7 into minus 7. Can you please draw this and compare your results to this diagram? Another signal that we will deal with a lot in this lecture series is the sinusoidal signal, the cosine and the sine. Those two functions are very, very important functions that we will work with, that we will use a lot. I'll start with the cosine function, which is, by the way, periodic function. When we talk about periodic functions, functions that repeat themselves, cosine and sine are the most popular examples, the easiest examples, the simplest examples for periodic signals. The equation for the cosine is x of t, a cosine 2 by ft plus phi. Or you could say a cosine omega t plus phi. From that equation and that equation, which gives you, by the way, this diagram, this is the very popular diagram for a cosine, you understand that the cosine has three parameters. There is this parameter a, which we will call the amplitude A, and we have this parameter f, the frequency, which could also be represented as omega. Omega is 2 by f. Both of them are called frequency. I'll give you more details in a second. And then you have this phi here, which is the phase shift. So please remember, there are three main parameters that describe a cosine. If you want to write down the equation for the cosine, you have to think about those three parameters: the amplitude of the cosine, the frequency of the cosine, and the phase shift. Before we discuss those parameters, let's look at the sine. Here is the sine function, which is also periodic. It repeats itself. This is the equation for the sine: a sine 2 by ft plus phi. Similar equation, just sine. Or you could say a sine omega t plus phi. Again, three parameters that describe the sine. This is the shape of the sine. Notice that starts at 0 here. This is slightly different than the cosine, which, as you can see here, starts at the full amplitude a, and then goes to 0 and goes up again and so on in a periodic fashion. But the sine actually starts at 0, goes up and down, and so on. Let's talk about those three parameters: the amplitude, the frequency, and the phase. First, the frequency. To understand the frequency, remember that this function, sine, and also the cosine, repeats itself. It repeats itself every period t. Notice, for example, after this behavior of the function, it repeats itself again, and then repeats itself again, and repeats itself again. And this time interval after which the function repeats itself is called the period in seconds of that periodic function. I'm going to use the symbol capital T to represent the period. So the sine and cosine, which are periodic signals, they repeat themselves every period of time t in seconds. If you want to calculate the frequency of those repetitions, how fast those repetitions happen, you have two choices. You could use f or you could use omega. What is the difference? The frequency f, which we call ordinary frequency, or the number of oscillations per second, or the number of cycles per second. How many cycles do we see per second? That's measured in hertz, and we call it f. How do you find it? The equation is simple: 1 over the period. Because you have one cycle every period t. If you divide 1 by t, or 2 cycles by 2 periods, or 3 cycles by 3 periods, or 4 cycles by 4 periods, and so on and so forth, what you get is how many cycles per second do you have, and that's called the frequency, or f in hertz, of that cosine or that sine or that periodic signal. However, if you multiply f by 2 pi, what you are doing is calculating the frequency in radian per second. This is what we call the angular frequency. The angular frequency, or the rate of change of the function argument. The rate of change of the function argument. Because the derivative of this argument, if you take the derivative with respect to time, rate of change, you get omega, and the rate of change is how fast the signal changes. So you get omega, which is 2 by f. Two representations for the frequency. Sometimes we use hertz because it's easier. Sometimes we use radian per second because it's easier. And I will stick mostly with radian per second because it makes the equations a little bit easier for us in Fourier series and Fourier transform. The other important parameter for a cosine and sine is the amplitude. The amplitude is the peak deviation of the function from 0. So this distance here, this value here is the amplitude of the sine function. And this here, this is the amplitude, it's the peak deviation of the cosine function. Please notice sometimes we use this distance between the peak and the peak. We call it peak to peak value, which is twice the amplitude, 2a. If you say peak to peak, it's 2a, but if you say peak or the amplitude, it is the value of a. And it's this a that you can see here. If you make a 1, the cosine will go between 1 and minus 1, and the sine will go between 1 and minus 1. The third and last parameter is the phase shift phi here and phi here. What is that for the cosine and sine? Well, the phase shift phi, which is measured in radians in those equations, is the shift from the reference signal that I've shown you a minute ago. If you shift to the right, the phase shift is negative. But if you shift to the left, the phase shift is positive. I'll show you here an illustration. The reference signal for the cosine is the red curve. So x of t, a cosine 2 by ft, or a cosine omega t, notice it has 0 degrees or 0 radian phase shift. It is the reference signal. It is what we know to be a cosine. However, if I introduce another signal, a cosine 2 by ft minus theta, where theta is positive, but I have minus here, which means I'm introducing a negative phase shift minus certain amount of radians. Same thing here, a cosine omega t minus theta, so I want to introduce a negative theta, say minus 0.1 radians phase shift. What happens? You get the blue line. Notice the blue line is the same as the red line, but shifted to the right. Because you have minus theta, you're going to shift to the right by an amount of theta radians. If you do that, you get a phase shift. We say the blue signal is phase shifted from the red signal, which is the original cosine. If your phase shift is plus theta or plus 0.2 radian, then you shift the blue signal to the left, not to the right. And you'll appreciate this shift to the right and left later on when we talk about the time shifting property. All right, quick summary. What changed between the red curve and the blue curve? The red curve is cosine and the blue curve is another cosine. What did I change? You have three parameters. You have amplitude, you have frequency, you have phase. What did I change between the red cosine and the blue cosine? Well, hopefully you understand. Here I changed the amplitude. I increased the amplitude of the blue curve compared to the red curve. I did not change the frequency because I did not change the period. The period stayed the same. And I did not change the phase shift because notice they both start at the same point. The blue curve is not shifted compared to the red curve. However, I did something else here. What did I change between this cosine and this cosine? I did not change the amplitude here. If you compare the amplitude of the red, it's the same as the amplitude of the blue. What I changed here is the frequency. When I change the frequency, what happens is that the period changes. So, question for you guys, is it higher frequency here or lower frequency? What did I do here? You can pause the video if you want. Well, the answer is obvious. What I did is reduce the period for the blue curve. Once I reduce the period, the frequency increases in hertz and also the frequency increases in radians per second. They are related to each other. Finally, a few examples for the phase shift in radians for the cosine and sine. One cycle in a sine function or one cycle in a cosine function is actually 2 pi. It's like going through one circle. It is 360 degrees or 2 pi. So if you have one full cycle for the sine, you're getting 2 pi radians or 360 degrees. If you have half a cycle, you're getting pi or 180 degrees. If you're going 1/4 of a cycle, then you have pi over 2 or 90 degrees. The same thing can be said about the cosine. If you take one full cycle here from this red curve, you get 2 pi. But if you take half a cycle, what you're getting is 1 pi, which is 180 degrees. If you're taking only 1/4, 1/4 of the cosine, that's 90 degrees. So if I say to you guys, let's compare this sine with this cosine, what can you see? Well, you should be able to recognize that the sine and cosine, they look alike. And I sketched both the red curve, the cosine, and the blue curve, the sine, to be the same amplitude and the same frequency in this case. What they are different in is just one thing, the phase shift. Notice that the sine is just like cosine, but phase shifted to the right. How much phase shift to the right? Well, we can clearly see that it's 1/4 cycle. If you go from this point to this point, that's 1/4 cycle of the cosine or 1/4 cycle of the sine. That's why this equation is an important equation to remember. A sine omega t is the same exactly as A cosine omega t. See, the same frequency, same amplitude, but there is a phase shift. Because the sine, which is the blue curve, is shifted to the right, I have minus pi over 2 radians. That's the shift to the right. And that's why A sine is equal A cosine omega t minus pi over 2. This is, by the way, the correct mathematical notation. Sometimes we write minus 90 degrees because it's easier for us human beings to think about degrees. But to be honest, this is not perfect because this is degrees and this is radians. And you cannot just add degrees and radians. This is the correct way to write the equation. But I'll accept this because a lot of people also use it, especially in electrical circuits. How about if we think about cosine, A cosine omega t? Can we write cosine in terms of sine? Yes, because cosine is just like sine, but it's shifted to the left. Shifted to the left by a 1/4 cycle, which means A cosine omega t is just like A sine omega t plus pi over 2, plus 90 degrees, which is shift to the left. Remember, minus, shift to the right, and plus, shift to the left. If you want to practice this, please look at this diagram and give me the answers for the following. What is A cosine omega t minus 180 degrees or minus pi? What happens if I take a cosine and I shifted? Minus means shift to the right. And then try the other way around. What is A cosine omega t plus 180 degrees? What is the answer? Is it cosine? Is it sine? Is it minus? Is it plus? What is the right answer? And try also to do it for the sine. What if I take a sine omega t and I shifted minus 180 degrees, or I shifted plus 180 degrees, or minus pi or plus pi? Or what happens if I shifted minus 270 degrees or plus 270 degrees for the cosine and sine? This is a 3/4 or 3/4 cycle shifting to the right or shifting to the left. Please try to figure out the correct answers for those phase shifts. All right, more exercises. Can you recognize this function? I'll give you a hint. It has to do with the sine and cosine, but it's neither sine nor cosine. Have you seen this function before? What is it? Also, another exercise for you guys. I sketched two important functions as well. This red curve, which goes from minus infinity and then crosses 1 here and then increases slowly. So it's increasing very fast from minus infinity, crosses 1, and then goes up slowly. And this function, which starts at 0 and then increases slowly, but more than the red curve. The blue function is a certain equation that you're familiar with. What is it? And the red curve is also an equation that you're familiar with. What is it as well? You can tell me in the comments section. I'll stop here for now. Thank you for listening. We'll talk about more important signals in the next lecture. Please ask any questions that you might have in the comment section. See you later. Bye-bye.